Our lesson today is called Integer Sequences, and we are now starting Chapter 6, Linear and Exponential Sequences. For the opening exercise, there's a situation with Mrs. Rosenblatt where she gave her students what she thought was a very simple task. What is the next number in the sequence 2, 4, 6, 8, ... So Cody has an answer, Allie has an answer, and Suri has an answer. I would like you to pause the video and take a look at their responses, and then answer questions 1 through 3. When you are ready, you can resume the video to go over the answers with me. Okay, so Cody said, I am thinking of a +2 pattern, so it continues 10, 12, 14, 16. Allie is saying, I am thinking of a repeating pattern, so it continues 2, 4, 6, 8, 2, 4, 6, 8. And Suri says, I am thinking of the units, digits, and the multiples of 2, so it would be 2, 4, 6, 8, 0, 2, 4, 6, 8. So number 1, are each of these valid responses? Answer should be yes, they are all some sort of pattern. Now in number 2, what is the 100th number in the sequence in Cody's scenario, Allie's scenario, and Suri's scenario? So for Cody's scenario, we're looking at a situation where we're doing 2n, we're doubling. So 2 times 100 would be 200. Say for Cody, it's 200. If we look at Allie, if we notice the pattern, every fourth number is an 8. Luckily for us, 100 is also a multiple of 4, so that means Allie's term is an 8. If you look at Suri's, the 5th term is always going to be a 0. 100 is a multiple of 5, so we know that the 100th term is going to be 0. Now in number 3, what is an expression in terms of n for the nth number in the sequence in Cody's scenario? Probably that you might have struggled with this, so hopefully you did the best you could, but here's what you should have gotten for an answer. And you can see I wrote it up above for Cody. It would be 2n because you're doubling. Okay, he said a +2 pattern. We're going to add this. Cody's pattern is a sequence. It's going to be new vocabulary for today. You're going to also put that it starts with n equals 1. So underneath that, it says the main point of this example, even though there is nothing wrong with starting sequences at n equals 0, or any other integer for that matter. So I want you to think about when we're doing y equals mx plus b and we find out what's across from 0 to get the y-intercept, okay? But we're going to agree that during this chapter when we're working with sequences that we're always going to start our sequences at n equals 1. Third, we're going to take a look at example 1 with Jerry. Jerry has thought of a pattern that shows powers of 2 this time, not multiples of 2, powers of 2. That means we have a base of 2 when we're thinking about base and exponent. Here are the first 6 numbers of Jerry's sequence. They want us to write an expression for the nth number of Jerry's sequence. So for the term number, the first term that we had was a 1. Our second term was a 2. Third term was a 4, and I'm just looking at the list that's located up here. The fourth term was an 8. The fifth term was a 16. And underneath that, you can say that the 6th term was a 32. Now, let me show you what that translates to into writing it in a sequence format. For the first term, okay, we write A with a subscript of 1. It's read A sub 1, okay? Our first term was still a 1. Our second term would be written as A sub 2, which was 2. Our third term is A sub 3, which was 4. Our fourth term would be A sub 4, which was 8. Fifth term is A sub 5, which is 16. The sixth term would be A sub 6, which is 32. Now, another way you could write this, and you might see it, is in function notation. So in function notation, you would write f of 1, f of 2, f of 3, f of 4, f of 5, and f of 6, if you recall function notation back from chapter 5. Now, a couple of things to notice when you're trying to figure out the formula for this. Remember that we are starting at 1. So if I were to put down 2 to the first power, I would get a 2. If you look at the first row of our tables, the first term is not a 2. So that shows me I have to go back 1 to 2 to the 0 power, which is equal to 1, and then continue on with 2 squared equaling 4, and so on. So that's reminding us why when we write our sequence, we can't start at 0, we have to start at 1. So we're going to have to subtract 1 in the exponent to properly represent this sequence. So again, if I had started at 1, the first term would be 2 to the first, or 2. When I look in our tables, our first term is not a 2, it's a 1. So I have to take that 1 away from the exponent to get the right starting place. And we're subtracting the 1 because of the fact that we start at n equals 1. Okay, now in example 2, consider the sequence that follows a +3 pattern. Our sequence is 4, 7, 10, 13, 16. A says write a formula for the sequence using both the a sub n notation and the f of n notation. So if we make a quick table, actually, we have the term number and we have the term. And we'll do a few of these so we can see what's going on. Our first term in the sequence was a 4. Our second term was a 7. Our third term was a 10. And our fourth term was a 13. Now looking at this pattern, this looks more like a linear pattern. We're going to put that word over here. This looks a lot like trying to find the slope and the y-intercept. If I go up the table this way, I am adding 3 each time, while on the other side, I am adding 1. In addition to that, I could find out what is across from 0 by extending the table. If I extended the table up, I would have 0 and I would have 1. And that would give me my y-intercept. So when I describe this sequence, I can write it as a sub n equals, the slope of this would be 3, so that goes in front of the variable. The y-intercept would be 1, so +1. Or in function notation, you would write f of n equals 3n plus 1. It's important to write, though, again, that we're starting with n equals 1. If I switch to yellow highlighter, remember, the teal-colored highlighter I added to the table just to figure out what the y-intercept was. Our actual first term is a 4. So we have to make sure that we say that we're starting with n equals 1. Now in part B, it says, does the formula f of n equals 3 times n minus 1 plus 4 generate the same sequence? Why might some people prefer this formula? So we're going to take a look at it and see if I can simplify it to get it to look like the formula we came up with. So f of n equals 3 times n minus 1 plus 4. I'm going to distribute the 3, and I would get 3n minus 3 plus 4. And that would equal, by combining my like terms, 3n plus 1. So I do get the same exact answer as I got up above. Take a second and pause the video and think about the second question and see what you come up with. I resume when you're ready to see the answer. Okay, so the reason people might like this formula better is because it actually gives us some information without having to do any manipulating right away. If you look back up at our sequence, that number 4 is special because it was the first term. So we'll write 4 is the first term. And if you notice the other number in here, that 3 that pops out in front of the n minus 1, that was actually the pattern of the sequence. It was a +3 pattern. So 3 is the pattern of the sequence. All right, moving on to C. It says to graph the terms of the sequence as ordered pairs n comma f of n on the coordinate plane. What do you notice about the graph? And if you recall from up above, we have n and f of n. We have 5 terms, and they were 4, 7, 10, 13, and 16. So these are actually giving us our coordinates. Now, a couple notes about the graph. The x now becomes an n, and the y now becomes an f of n because we have these different labels. And we're going to plot these coordinates. Everything is going by ones, you can tell. So we have 1, 4, 2, 7, 3, 10, 4, 13, and 5, 16. So what do you notice about the graph? The points are in a straight line. Okay, so again, thinking back to what I wrote up above, it's a linear pattern. Now there's a special note that I do want to put underneath here about graphing sequences. Okay, so put note. A sequence is what we call a discrete function. Now that's just a fancy way of saying underneath that you do not, let's underline that, connect the points. Now think about that. We connect points when there's values in between. If this is a sequence, there are no values between 1, 4, and 2, 7. So they are just isolated points that we plot as coordinates only and we do not connect. Now at this point, if there is an activity posted for you to complete separately, you will please stop this video and complete that activity on your own. If there is not something posted, you're going to move on and try the practice questions. Okay, practice 1 and practice 2. Pause the video and then resume when you're ready to go over the answers. Okay, at this point, you've had a chance to try the practice. I have the answers filled in and I will go over them with you now. For A, it said to write a formula for the nth term of the sequence. Be sure to specify what value of n your formula starts with. So this was a -5 pattern, which means you have a slope of -5 with a starting point. Actually, if you work your way backwards to find out what's across from 0, which I can add down here to the table, if I were to go backwards, it would be 0 and 35. You're only going to use this to help you with this question up here to figure out your y-intercept. So that's how I got 35 minus 5n, or you could also have -5n plus 35. I gave you both notations for a sub n as well as f of n. And you can notice underneath, I did say starting with n equals 1. That's important to write. In B, using the formula, find the 20th term. You write the formula so that it's easy to find other terms in the sequence. Let's say I wanted you to find the 900th term. You're not going to want to write out that entire pattern. So you create the formula so that you can then just substitute in. I would want to find f of 20 or a sub 20, and I would just replace n in my formula with the number 20 to simplify and get -65. When I graph it, I gave you a pink table there with n and f of n. I should get a linear pattern that looks like it's decreasing. And remember, do not connect the points because it is a sequence. I've also changed my notation to n and f of n with my x and y axis. Moving on to practice 2, we have a sequence that follows a ×5 pattern. So this is very similar, and you might want to put this up here, similar to our first example where we had 2 to the n minus 1. So immediately you should recognize you're going to have a similar setup. Here, since it's ×5, you're looking at powers of 5. So that also might want to be something that you write down as a helpful. Okay, so you should have a sub n is 5 to the n minus 1 or f of n equals 5 to the n minus 1. Again, starting with n equals 1. You can tell that by looking down here at the table that you see me writing in green. The first term is a 1, not a 5. So if it was just 5 to the n, it would be 5 to the first, and we would be starting with 5. In B, you're just going to use the formula you created and replace n with 10. So you're doing 5 to the 9th, which is 1,953,125. And lastly, in part C, you had to graph the terms of the sequence as ordered pairs. So I gave you my table of values for my work. I changed my notation on my graph to n and f of n. And you can see here that it is not a straight line. And I would add that as a note for this one. Not linear. Okay, it is taking a curved pattern. And that concludes your lesson on integer sequences.